do another medium container with the most water. You're given an integer array height of length n. Okay, so this is height, and its length n. There are n vertical lines drawn such that two endpoints are I sub 0 and I sub I. Find the two lines that together with the x-axis form a container such that the container contains the most water. Return the maximum amount of water the container can store. Notice that you may not slant the container. Okay, this actually reminds me of a problem. I've solved this problem kind of before, years ago. Let's see if I remember it though. I'm wondering if there's a naive solution. The naive solution I think would be like n squared. Just check every single thing and find the max. What are we trying to return? The max amount of water a container can store. And so, yeah, it would just be 1, 2, 3, 4, 5, 6, 7, and this is 7 high. The above vertical lines are represented by an array. In this case, the max water contained is 49. Let's write a naive solution and then we'll think while we do that. I is less than height dot length I plus plus, or let j equal 0, I plus 1, j is less than height dot length, j plus plus. We'll say let max equals 0, return max. And so max equals math dot max of max, and then we'll have that term, and the other term is going to be j minus I times math dot max of height sub I and height sub j. Let's just see if that works at all. Alright, so we got 49. So my idea essentially here was we're gonna go through each and every single combination, and basically the volume that we can fit is going to be the distance between them times the shorter of the two. Of course, it's the shorter of the two. There's no way you could add more water than that. But obviously this is an n squared algorithm, which is not great. So I guess let's try to think a little bit more deeply here. What is this? Oh, you could time your... Interesting. Let's just like list out ideas. Is there a recursive way? Is there a way to use a map? Is there a way to use dynamic programming? Important note that we are currently n squared. So potential improvements could be n log n and n. I can imagine us being able to do maybe n log n, but I don't know about n. See, it might be easy enough to like find the two highest bars, but if they're too close together, that's a problem. Because you can have two really small bars that are really far apart that do better than two long ones that are really close together. So it's not that easy to just find the tallest ones. This is a medium problem, and I think there is an optimization, because I remember there being a better solution. I just don't remember exactly the solution. Oh, I'm not allowed to see that. Greedy. Let's submit it. I'm just curious how many people optimize. Okay, well, you do need to optimize, it seems. If you don't optimize, you won't even get past the test case. So if that's the case, most people are going to have optimized. So the question is how to optimize. Notice that you may not slant the container. In this case, area is blue, 49, 11. Do the constraints help us at all? They could be 0. There's always at least 2. Okay, so it's a greedy algorithm, and I'm not really like well versed in how to do greedy algorithms. Is part of the problem, at least. Because if we're here, is there any way to know that this is gonna be better, even if we like logarithmically divided the problem? I don't think that like going to the middle. I wonder if we can make like an assumption about the height of this. I think I'm gonna use a hint, maybe? Maybe this hint helps? Yeah, yeah, it's not efficient. Always move the pointer that points to the lower line. Try to use 2 pointers. Set 1 pointer to the left, 1 to the right. Okay. Alright, I'll try that. So basically we have let left equals 0, right equals height dot length minus 1. And I guess we'll say while left is less than or equal to right. less than right. And then we'll probably also keep max. And then we'll say max equals math.x of max and right minus left times math.min of height sub left plus height sub right. And then I guess if height sub left is less than height sub right, only move the smaller one. Always move the pointer to the lower line. So if we do this, we do this. Now, this is actually big O N? What the heck? It's right, minus. Oh, I don't even have the right syntax. Oh, no semicolon there. Okay. That's kind of crazy to me. I guess the idea is you are trying to prioritize being as far apart as possible. And so when you're focusing on that, the next best thing is to try to find something bigger. And so if you're going to decrement your width, the best thing to do is to increment your height if you can. It's not super intuitive. I would like to see what the third hint is though. Oh, there's a way to run it faster. I might just be getting unlucky though. Who cares about the n squared algorithm? Wow, I made it slower. Dang. Fine. You'd think that caching the value would be faster. Oh, I just keep getting slower and slower, what the heck? That's okay. I think I'm just getting unlucky. Let's look at other solutions. Yeah. I mean, the best solution, we have pretty much the same code. the next best solution. Same. Next best. Same. Same. The thing is, they got 0 milliseconds. Which is kind of crazy. Oh, J is n minus 1. I thought I saw 2 for some reason. Okay, so what was the third hint? Second hint was more helpful. But with this new code, it is big O-N, which is surprising to me. I think the greedy algorithm is pretty important. I'm curious the applications of it though. This will be something I keep in mind though, if I know that an algorithm is greedy, to use pointers. It's not super intuitive.